You're listening to a podcast from the University of Manchester.
This episode was recorded during lockdown. Please forgive any issues with sound quality. Hello and welcome to The Buzz. In this episode, we'll be running, jumping and diving into the fascinating world of animal robots. We'll speak to Dr Ben Parslew, a senior lecturer in the Department of Mechanical, Aerospace and Civil Engineering, who specialises in animal locomotion, unmanned aerial vehicles, robotics and computer animation. So I've done a little bit of research myself into this weird and wonderful world, and one of the things that struck me is the huge range of animal robots that we already have. And what I thought was particularly interesting is the names of some of these robots, with some of them being quite quirky, some quite funny. So I'm joined by Corey, and what I wanted to do was just a little quiz to see, Corey, if you're up for it, which of these names you think are real and which ones I've just made up.
Yeah, sounds good. What did I get last time? I got 4 out of 5 on the sustainable housing one. So
I think you did well, but there was room for improvement. So this is your opportunity. Okay, so let's play real or fake. So real or fake, the Velociroach.
I'm gonna go real. It sounds like a cool little robot.
You are correct. It is real. It's a tiny robotic cockroach. It's just 10 centimeters long,
Wow.
but it can actually run 2.7 meters per second, which makes it one of the fastest robots of its size.
Yeah, definitely. That's so quick.
I know, rapid. Okay, real or fake, the Crabster.
The crabster. Okay. That sounds like a made-up name that you've made up, so I'm gonna go with fake.
It does sound like something I make up, but someone else has made it up, and it's real.
Wow.
Yeah.
Wow.
It's a huge robotic crab that's designed to scuttle along the seafloor, and it helps to explore shipwrecks. And I've seen some pictures of it, and it's very impressive.
It sounds terrifying.
Yeah, I know, it looks terrifying as well. Okay, next one. Dolphin Lundgren.
Dolphin what, sorry?
Lundgren.
Lundgren.
You've heard of Dolph Lundgren, right?
No, I haven't.
Oh,
So I have
no.
no idea what you're talking about. It's definitely fake.
He's the bad guy in Rocky IV.
It's
The
definitely
actor. You're right, it is fake. Okay, next one. Real or fake? Octopus Prime.
fake. That's a good name. I want it to be real, so I'm going to go real. Very good name.
Thank you, I just made it up.
No,
It's fake.
that is very good. If anyone is making an octopus robot now, I think they should name it Octopus Prime.
Yeah, I think they should, and they should give me credit for it as well.
Yeah.
Okay, this one kind of on a similar vein. Aqua Jelly.
Aqua Jelly. I'm going to go, that's real.
You're correct. That one is
Yeah.
real.
Sounds just boring enough for it to be real.
Yeah, it's an artificial autonomous jellyfish that emulates swarming behavior.
Okay, cool. Again, sounds terrifying, but cool.
Yeah, from the pictures as well, it's really impressive, but again, quite scary. So the next one is R2D Tuna.
That's also very good. Oh dear. I think you've made that up based on the solidness of the last pun.
You're learning your lessons quick. That is fake. I've made that one up. Okay, this is the second to last one. So, real or fake? Spark the Aardvark.
I think it's real, and I think it's going to be good at smelling stuff.
It's fake.
Oh, no.
But if it was real, it'd be fantastic at spelling stuff. But I just made that one up.
Oh,
So
not doing very well there.
unlucky. You're not doing too bad. So the last one is real or fake? Robo Bee.
Robo B. Yeah, I think that's real. Again, I think it's just boring enough for it to be real.
That is real. You finished strongly. It's an autonomous flying micro robot, and it's only about half the size of a paperclip, so it's tiny.
Wow.
And I kind of wanted to include that one because it fits in with the name of this podcast.
Yeah, maybe it can be our mascot. The Buzz is Robo Bee.
Maybe our scary little mascot. Okay, so you got 5 out of 8, which I think is similar to what you did last time. So consistent is the word. Great. So someone who knows lots about animal robots is Dr. Ben Parslew, and here's our interview with him.
Why are robots so hard to get them to move naturally?
Well, I think it depends a lot on the type of movement that you want the robot to do. So some robots just have wheels and need to move around on a flat surface like a road or a pavement or a warehouse. And that's relatively easy to do. We can do that quite well already. But if you're talking about a robot that has a more complicated structure like legs and you want it to move around like a human, that's really quite challenging. And there's a number of reasons for it, but we've made some progress in it, but it is still an unanswered question about how we get those robots to move naturally. I think that the biggest challenge there is balance. So something like a humanoid robot that has just 2 legs trying to walk like a human, it has to do all kinds of things to stay balanced. As we as humans, we do all things going on behind the scenes without us thinking about it. So we have our senses to help us. So we're using balance sense, we're using acceleration, we're using the tactile sensors in our feet to measure what's going on and making little corrections all the time. Whereas if you get a machine to do that, you have to try and emulate all of those different processes at the same time. So it really is a lot of different things you have to fuse together to get robots to move naturally, like humans or other animals.
So what animals are we currently using for models as robots?
So for walking robots, probably the big 2 types of animals we use are humanoid, humans, 2-legged things, or quadrupedal animals, things with 4 legs. And with those, it's probably dogs are the main source of inspiration for 4-legged animals. Cats get a bit of a look in, but not as much as dogs.
Sure. And why would we? I guess why do we want them to move like humans? Do we think that's the best way that people like? Is that the most efficient way of moving, or is it just because we want them to be more like human?
Yeah, that's one of the big questions in this field: is why do we want to move like humans? I think we certainly don't think that humans are the best. So we don't do things better than is possible by any other means. But one of the advantages, if you can get robots to move like humans, it means you can deploy those robots in our existing infrastructure. So if you can get a robot, say, to climb stairs, it means you can put that into any building and the robot can climb the existing stairs. You don't have to develop a new type of system to move the robot around. You just use what we already have. If a robot can hold a handrail, then great, they can use handrails. If they can use door handles, then we can use our existing doors. We don't have to design a new type of door. So it is sort of practical reasons that drive us to having human-style robots.
Is using animal robots a relatively new idea, or has it been around for a little while?
In some way or another, it's been around for quite a long time. I think even if you go right back in history to some of the sort of early sort of philosophers and scientists were using whatever was in the world around them to get ideas about science and physics and just how things work. And going back, say, if you take the example of aviation, the early aviators, people looked at birds and flying animals to try and get ideas of how they could replicate that in machines. So whether they were actually robots or not is hard to define, but you could say at least people have been taking inspiration for animals for machines for centuries.
Cool. And so I guess like you were saying about how we might develop them for situations where humans currently do the job and therefore would bring in robots. Because in my head, historically, robots have been like on car manufacturing plants or like in a big warehouse and they're just picking stuff up. Are we now moving into a time where they're doing more sophisticated things?
Yeah, I think we are. So those ones that you mentioned, the kind of car assembly robots, those have really well understood how they work now. And so they get put to great use in putting cars together. But now we're in an age of what we'd call mobile robots. So these are robots that can actually transport themselves around an environment. So they're no longer stuck to the floor. They're actually mobile. They can climb stairs. They can climb obstacles. They can open doors. They can move things around. So that's what the sort of current state of the art of robot research is at the moment, is trying to get robots that are actually mobile.
It sounds really fascinating. What kind of specific examples of animals kind of have already been developed and are already being used? And are there any that you can see coming up soon?
I think one of the really successful ones over the past, say, 5 years has been the quadrupedal, the four-legged dog-style robot from Boston Dynamics. This is the one that we've all seen online in memes and things, where it runs and jumps and skips and dances and does all kinds of fantastic things. So theirs isn't the only one. There's a number of research groups around the world that have developed these quadrupedal robots, and they seem to be pretty successful. And one of the areas that they're targeted for use is in nuclear decommissioning environments. So these are, nasty environments where we don't want to send humans because they're really dangerous and really messy. They're really cluttered, so there's all kinds of junk everywhere. So you can't send a normal wheeled robot. You need to have something that can climb and move over obstacles. So it has to have legs, and if it has 4 legs, that offers a bit more stability than having 2 legs. So I think that's been a really exciting area of research in the past few years, these quadrupedal dog-style robots and deploying them into really nasty environments.
Sure. I guess you might not know, but are these like robots, are they controlled by like probably not a remote control, but like are they controlled by a human, or are they kind of given a bit more, are they machine learning and they're doing this on their own?
Yeah, there's a full kind of scale of autonomy. So at the very low end, it is, as you said, at the very low end, most of them have some ability for a human to put in an input with a kind of remote control and guide the robot around as it wants to go. So most robots can operate like that in some sense. But then you can usually layer on different levels of autonomy, where you might say, put in some high level command, like go from this part of the room to that part of the room, but you don't tell the robot exactly how to get there. And it has some onboard intelligence that figures out the best way to get there. It could be the safest way to go, the quickest way to go, the most efficient, or whatever. And then at the very other end of the spectrum, you have something that's fully autonomous, where you don't give it any information at all, and it just decides what to do. So with every type of robot, from a walking robot to, say, a driverless car, we have to decide whereabouts on this sort of autonomy spectrum you want the robot to be.
When we're thinking of kind of scale of size, kind of how small to how big are we going with animal robots?
You mean the physical size of the robot, right?
Yeah, physically.
Yeah, this is a really nice one, actually, and this is one of the really, really tough questions to answer. Is how big you can make a robot and how small you can make a robot, and it's a really difficult one. And people care about both ends of the spectrum. So for really small things, there's a lot of people interested in insect-style robots, both crawling and also flying. So there's some really nice examples from Harvard University of their RoboFly. I'm not sure if you've seen that one, but it's a fly-sized robot, 2 wings. It flaps its wings and it can fly around like a fly. And there's also some dragonfly-style robots that do a similar thing. Even smaller than that, some people are trying to make sort of micro dot-style robots that can crawl around and might be used to inspect electronics or engines and things in the future. So really tiny things. I think that seems doable. Really large things, when you operate at really large scales, you run into this problem where as things get bigger and bigger and bigger, they get heavier relative to the amount of power that they can produce and the amount of force or torque that the motor can produce. So you do reach this kind of upper limit of how big something can be, and you see that in robots but also in animals as well. So there's this kind of question about, why is the biggest animal an elephant or a whale? Why don't we have things that are even bigger than that? And you get exactly the same problem, that the mass of the animal increases faster than the force and power that its muscles can produce. So you do get an upper limit. So what it is in robots at the moment is unknown. So I don't know how big they could possibly be, or what the biggest is, but it would be interesting to see whether you could make an elephant-sized robot or a whale-sized robot.
Sure. And in terms of like economies, is this something that's fairly cheap to make? I mean, it will depend on the robot, obviously, but do we see this kind of being, employed in the near future in I guess a supermarket or something, a buddy helping you around the shop?
Yeah, I think the buddy style robots is something that's quite a sort of key application that people are interested in. So whether it's to help with mobility or whether to help with sort of companionship, so this buddy style of robot is, I would say, quite high up the sort of technology readiness level. It's sort of they're almost ready to go, and in some places they are being used already. The cost varies so much between the different types of robots. So some of the things you see in the sort of more cutting edge research things, they are perhaps quite a way off. They could be 10 or 20 years off being able to be mass produced and used widely. Whereas the robotic arms, even though they're quite expensive, they are used in all kinds of industries now. So the cost really does depend on the sort of state of the art, how close to the state of the art that robot is.
Are there any places in the world that are creating these robots? Most of them, or is it kind of spread around the world?
It's fairly spread, but there are hotspots. So I think most people probably have this idea that Japan is famous for robotics, and there is some truth to that they have really progressed a lot in Japan, and particularly that the example you mentioned before about this sort of buddy style robot, that class of robots seems to have accelerated a lot in Japan. And also they've done some really impressive work on humanoid mobility, walking robots. But walking and locomotion, there's been some a big acceleration in the US. Some of the really fundamental work was done in the US on making walking robots, and whether with 2 legs or 4 legs or more than 4 legs. And then there's some big things going on in the UK and in Europe. So it's fairly spread, but you do get these hotspots coming up. You even get certain research centres that are really famous for swimming robots that are particularly focused on fish-inspired robots, for example. So it's quite hard to say exactly where the trends are, but you do get these little hotspots popping up.
And I guess what are the challenges for? What are the big challenges in robotics at the moment to improve these robots?
There's technical challenges that are sort of we've made some progress on. So for walking robots, the balance and stability is always a big challenge. And first, it was just getting them to be able to walk around on flat surfaces. Even that was difficult. Now we can pretty much do that. Now the new challenge is getting them to move in more uncertain environments. So if you wanted a robot to go and walk around a street where there's obstacles and unsteady pavements, or if you wanted it to venture beyond an urban environment out into the countryside where there's rocks and hills and things that are all messy and nasty, that's quite a big challenge. So this kind of uncertainty in the environment is one of the really difficult things to handle with robots. If you know exactly what it's going to encounter, where it's going to be walking, how steep it has to climb, if you know exactly what's going on, it's okay. But whenever there's uncertainty, that becomes a really challenging thing. So that's one of the technical things. And the sort of more social aspect is sort of acceptance of robots and social uptake of them. That's still a big challenge, is understanding how well people are going to accept having robots in their lives. So in some cases, the technology is already there. If we think about something like drones, we have the ability to fly drones and deliver packages, and that's there, and it's been there for quite a while now. But we don't see drones delivering packages in our cities, and that's related to social issues and health and safety and these kinds of things. So it's not a technology problem as much as being sort of social acceptance problem.
It sounds really interesting how many different types, like the idea of a robot fish is kind of mind-blowing to me. Do you have any particular kind of animal-based robots that are your particular favourites, or ones that you're quite kind of keen to see developed more?
Yeah, I guess that I do have some. I probably shouldn't have, but I do have some favourites. So one of the things. So my own personal passion is on flying things. So my background is in bird flight, and so I'm interested in that area of robotics as well. So one of the things I'm really keen on at the moment is this idea that traditionally robots, we designed them so that they tended to avoid all obstacles at all costs. You just avoid hitting into anything. But there's been a more recent movement in robotics now that robots have to interact and have to be able to touch things if they're going to work in our world. So with birds and flying robots, one of the things I'm interested in is how you can design flying robots so that they can interact with the surroundings, so that your flying robot can brush past the corner of a building, or can touch another robot, or can even touch a person without damaging the person, without damaging the robot. So I'm quite interested in that area. So birds and flying things are one of my favorites, and the movement in research in that area is having robots that can engage or touch their surroundings. But I do have a couple of other favorites. So things that can smell really well. So I'm interested in smelling robots. So this process called olfaction, which is smelling. Animals that can smell really well, like dogs, are a good source of inspiration for making robots that can sniff things out. So it's quite surprisingly, it's quite a big field actually. These sniffing robots or sniffer dog robots. So I've got a big I'm a big fan of those as well. And then the other one, anything that can jump really well. So I do quite a bit of work on jumping robots. So animals that can jump really well, from things like frogs to kangaroos to even birds that can jump really well. They're all personal favorites too.
Sure. It reminds me of, isn't there like a robot Olympic Games or something where they compete? It might not be the Olympics, but the robots compete against each other in like maybe the 100 meters sprint or something.
Yeah, there's quite a lot of these competitions actually where they give a certain tasks for robots to compete on, and sometimes it's a sort of sporting challenge, so they get them to do hurdling or race around a track or something like that. And then there's other ones where they give a robot a sort of a practical challenge that needs to be solved, like design a robot that can stack 100 bricks, to see if we could make robots a future for civil engineering. Could we have them as a way to actually build buildings? So they'll set these challenges where you have to complete a certain task. And another one is cleaning windows. Can you get a robot to clean a window? So that's often attempted with flying robots, is can you get it to fly up the side of a skyscraper with its little squeegee sponge and its bottle of water and try and clean a window, digging holes, opening door handles, picking up boxes, all of these kind of practical things that we do in our daily lives. That pretty much all of those has been given to robots as some kind of challenge to compete on.
I'm really intrigued by the sniffing robots. I know, obviously, you just mentioned there about robots cleaning windows. That's a very kind of obvious practical application. For things like the sniffing robots, what could that potentially be used for?
So one of the practical applications is trying to track the sources of chemical spills and plumes. So if somebody was to, say, drop some chemicals indoors or outdoors, you want to be able to safely tell all of the nearby people to avoid where the chemicals are going and go to a safe area. So one of the things we've got in mind for sniffer robots is to be able to measure the pollution in a certain area. So it could be a chemical pollution in a certain environment, and automatically track where that's come from and where it's going. So you can then warn people to get out of the way. So it could be for really toxic things like chemical spills in labs or even in cities, but it could be for other things, like if you've got something burning in a city, you've got a fire and you want people to go away from the fumes. So you could use sniffer robots to track where that plume of smog, of smoke is going to tell people where they need to go to be safe. It can happen at quite small scales. You can have something in a room or outdoors in a city, or even at much larger scales, like a sort of county or country level scale, where perhaps you've got a plume coming in from, say, a forest fire, and you want to tell people in an entire city where they need to go to. So it happens at all different scales. So that's why I find it really interesting, is the physics works at really small scales and at really, really large scales.
That's really cool. I was just thinking then, I guess what's the difference then between, say, a autopilot plane and a robot? Because you were talking about animals learning to, having birds that become robots and then they can fly and stuff. Is there a distinction then between like things like autopilot on a plane and a robot, or the kind of just, is that a grey area and it's kind of both?
It's a really grey area actually, and when a machine is a robot and when it's not is really undefined, and we don't have a definition for what a robot is. So we could say, is a car a robot? It nowadays has some level of intelligence. It does various things like temperature control. So does that make it a robot? Or my pair of scissors, is that a robot? So it has a sort of mechanism, but it doesn't have any intelligence to it. I think generally it's generally accepted now that if there's some level of decision making, or at least potential for decision making in that machine, then that becomes a robot, or you could call it a robot. Where if there's not really any potential for decision making, like a hammer or a pair of scissors, then that's probably not a robot. The example you gave of an autopilot, there is certainly some kind of decision going on there where it knows what it's got to do, and it has to figure out how it moves its propellers in order to be able to fly to that location. So there's some kind of automated feedback and decision making going on there. I think in that case, I would class it as a robot.
Is there like a conscious effort to make these robots kind of look like animals? Because obviously I guess the main focus is to make them behave like animals. But is it, in my mind, I'm thinking of kind of a bird, like a metallic bird. Would it look like say a bird with wings, or is that not so important?
Quite often it's not important. Quite often it's more about function rather than form. So you might want to say, for example, if you take a bird and you want to look at maneuverability, birds are incredibly maneuverable, much more so than drones or aircraft or anything that we can make. So if you want to use a bird as a source of inspiration for maneuverability, you might look at how it does it, and you might try and emulate that in the machine, but that doesn't necessarily mean covering the machine in feathers and giving it a beak, so it doesn't always end up looking like a bird, and generally they don't. Generally, you just want to try and emulate the function without necessarily emulating the form. There is a time where that kind of flips on its head, where you only really care about how it looks and you don't care about what it does. So the buddy robots is an area where you might want them to look like a human. If you have a humanoid robot and you want it as a companion, the function might be that it has to look human. Another area where you see that is when people are using robots for sort of ecological surveying, for surveying animals in the wild. So you get this in some TV documentaries, and you're starting to get it in scientific research as well, that if you wanted to survey a population of, say, penguins, you might want to do that using a robot, and you might want the robot to look exactly like a penguin so that it doesn't disturb the other penguins. So then you get a more representative survey. You don't disturb them, you get what they're really doing naturally. And this has been done with land animals and also with flying things. So there have been some examples of bird-looking robots that are there to try and study other birds or animals on the ground, but without disturbing what's going on around them, so you look like a bird. So that's quite an interesting area, I think, where those ones probably perform not so well in terms of how well they can fly or how well they can move, but their job is really just to look like the thing so that it doesn't disturb that particular animal.
This all sounds crazy. Like in my head, going into this interview, I was thinking, oh, we'll have, maybe you talked about delivering drone parcels via drone. I was thinking that's like 15 years away. It wasn't like you're saying we could do that now, which is social issues. How far away do you think kind of these, I guess, buddy or even like a robot pet, those kind of commercialized consumer products, do you think they're kind of coming soon as well? Or do you think it's still mostly going to be used for research and then maybe further down the line?
I think robot pets, they've already been actually trialed to varying degrees in real environments. So there have been studies done with people trialing robot pets and examining the human response and seeing how it compares to a real animal. So that's quite soon, I would say. And that's one of the areas where perhaps you don't need the robot to be quite as sophisticated as you might imagine. It might just be a robot that sort of resembles or feels like the animal, but it might not have to run around or move or have all the same functions as the animal. So I think that's an area that's coming pretty soon, actually. So we'll expect to see that in the relatively near future, the next few years. It's hard to judge the uptake of them, how widely we'll see them. It could be that they're used in very specialist applications, or it could be that within the next 5 years we all own a robot dog in our house. That's possible, but I think it will be, to begin with, they'll tend to roll out in more specialist areas.
It sounds like the potential is absolutely huge. I was just wondering, what examples have we got of the work that's going on at Manchester towards animal robots?
Well, I think one of the areas I touched on previously was this idea of nuclear decommissioning and working in nuclear environments, and that's a pretty hot topic at Manchester. So we're quite strong on that. There's various researchers and groups working on this. So there's been a range of different robots being used. One of the ones that I've seen is sort of resembles a snake-style robot. So it's something that can be folded up or unfolded to form a long and slender shape. And the reason it can form that shape is so that it can get access to these certain decommissioning environments where there's only very small entrances, very small access ways. So Manchester has worked on some snake-style robots that can be threaded into these nuclear environments and explore them and do measurements and characterization and things like that. So I think nuclear is quite a hot topic for Manchester University. Our group is working on the sniffer robots that I mentioned to you about. That's certainly more fundamental at a lower TRL, but it's something we're expecting to grow. And we do have quite a lot of experience in aerial robotics in drones. So in the applications for drones, in the design of new drones. So that's an area that we're also quite hot on as well.
What is TRL?
Oh, sorry, I should have said that. So TRL's technology readiness level. So when things are really low TRL, it means you've thought of the idea, you're doing it in the lab, it's all quite fundamental. And as you climb up the numbers of TRL from 1 to 3 to 5 and so on, as you get up to the top level, that means it's a product that's basically ready to be sold. So different technologies, usually they start off slow down and gradually climb up the TRL level. You do sometimes get things that just jump straight to the top, and it requires very little development to make it a product. Robotics is probably a field where it takes quite a long time, I would say, to increment up through the different stages. So we've had, robots in one form or another for, 50, 60, 70 years. But we don't all have them in our houses just yet. So you can see it's been a relatively slow but steady progress, I would say. And it's had quite an acceleration in TRL over the past 5 to 10 years.
You talked about how your background was originally in animal physiology. Maybe talk a bit about that, and then how or why you transitioned into robotics.
Okay, sure. So my background, well, originally I was actually in aerospace engineering. So I've come from an aerospace background. And then I had an interest in flight of all different kinds. And then for my PhD, I focused on bird flight. So I was really interested in birds and maneuverability and how birds can manage to do such great things that we can't do with machines. I mean, even the kind of humble pigeon that you see in the street, they're more maneuverable than our best drones and our best aircraft. And I found that quite interesting. So I studied birds and aerodynamics in my PhD, and that gave me a bit of an interest in animals in general and movement in particular of animals. And I think that sort of naturally led on to this idea of whether you can recreate those as machines. So, for example, the foot of a bird is a really interesting thing where it's quite a complicated mechanism and it's really quite adept. So birds are really, really good at gripping, and they can do lots of different tasks with their feet. So they use them to walk on, but they can also pick things up, whereas we humans just use them to walk on. We can't really pick things up very well with them. So I thought that was quite an interesting thing where it acts and looks like a machine, a bird's foot. So I was thinking, maybe that would be a nice thing to try and emulate in a real machine. And then you look at other function of animals like jumping or running, and you realize that actually they can do all of these wonderful things, but machines really are quite good at rolling on wheels and are okay at walking, but not that great. And some of them can sort of run. So whether there's any kind of clues or tips we can glean from how animals move to try and make our machines a little bit better. So it was mainly that idea of using animals as a sort of source of inspiration for making better machines. That's where it came from. The sort of flip side of that is that I really like the idea that you can't just copy what an animal does to make a really good machine. And looking in aerospace, that came up in particular, where the sort of early aviation pioneers tried to copy birds, and they were a complete failure. Like those early videos that you see of sort of flapping wing aircraft that pull themselves to pieces. So that was an example where you just try and copy what an animal's doing to get the same function. We copy a bird so we can make a machine that flies. That doesn't work at all. And it was only really when people really dug deep into all the different functions that a bird has, when you can pick out the individual bits that you need to copy. So we realized that you need to copy roughly the approximate shape of a bird's wing. You need that, but you don't need the feathers, and you don't need it to flap up and down. So that's really why I gained an interest in this field, is that you have to take, or you can take, a few ideas and a few hints and sources of inspiration from animals, but you can't just naively copy them and expect your machine to work. So that's why I find it really interesting. It's almost like a bit of detective work to pick apart which bit of the animal you want to try and borrow and which bits would just be better to ignore.
Could it be that robots are developed that use different parts of different animals, almost like a hybrid machine? Is that something that could happen?
Yeah, it sounds a bit unusual, but it could, and it does happen. So there's been some nice examples in locomotion. One of the challenges is you want to be able to move around, but then usually you want to be able to pick something up as well or do something else. Just moving around isn't usually enough to do your complete task. So these four-legged quadrupedal robots that I mentioned previously, they were developed, firstly, they could just move and walk around, but now there's been some examples of adding a manipulator, a sort of robotic arm to the top. So you end up with this funny looking four-legged robot with an additional arm on top, so like a fifth limb on top of it. So the robot can walk around, walk upstairs, walk up to the door, and then the arm on top clasps the door handle and turns it and opens the door. So that was quite a nice area where you're basically taking a sort of human arm, or a human style arm and a human style hand, and then a dog style body and legs, and fusing those two things together, and you end up with this unusual looking robot, but that can perform quite a lot of interesting tasks.
So we touched on before animals that can fly, even animals that can swim. Are there any other forms of movement that is going on at the moment with robot animals?
Yeah, there's lots of different kinds of movements, climbing, scrambling, skipping, you name it. People are working on all kinds of robot movements. One that I find really interesting, one that we have some people working on, is on jumping robots. So trying to make things that can propel themselves either really high up in the air or really far into the distance. So there's been a few different groups around the world working on this. One of the challenges people try and sort of overcome is trying to make the robot that can jump the highest. It's a bit of a sort of rivalry in the robotics community, is which robot can jump the highest. So that's quite fun. But one of the things I find really interesting actually is just thinking what would we really use them for? So if you have a jumping robot, how can that benefit us? So one suggestion originally was that I will use these jumping robots to be able to move around really cluttered environments. So if you're in a really messy area where the obstacles are too big for a robot to climb over, then you need to be able to jump to get over it. So that was one thought. But more recently, I think what's been realized is that a really promising application for these is in low gravity environments like the moon. So in those environments, something that can jump a small height on the Earth can jump much, much higher on the moon because of the lower gravity. And the moon is an environment where jumping as a means of locomotion, as a way of getting around, is actually really, really efficient. You see that even with humans. They tend not to walk on the moon, they tend to hop and jump around. It's just an efficient way to move. So we've been doing some work on developing jumping robotics specifically for lunar environments, for exploration. So being able to jump means that you can commute really efficiently around the moon, and it also means that if there's obstacles like boulders or ravines or things that get in the way, then you can essentially jump over them without having to worry about how you navigate around them.
That's really cool. The only other question I've got is, I guess, are you optimistic about the future of robotics and animal-inspired robots?
I am actually. Yeah, I'm really optimistic about it. I mean, that partly comes from the acceleration we've seen in the past few years of these types of things, but also in some of the up and coming areas in robotics. So one particular area that I'm keen on is soft robotics. So your traditional robot, you imagine it's made out of big chunks of metal all joined together by motors. But the newer wave of robotics are actually made out of soft, compliant, squishy materials. So that's a big and promising area of robots that it not only gives sort of exciting research projects to work on, but it also opens up this idea that I mentioned previously about having robots that can interact with our environments and with ourselves. So the idea that we could have these nice, safe, soft, tactile robots as buddies or working alongside us in offices or in factories, I find that quite an exciting and promising area for the future of robotics.
And that's about it from us today. A massive thanks to Ben for his brilliant insight into such a fascinating topic. Next month, we've got an equally exciting theme as we ask, what can we learn from the moon? We'll be speaking to 2 Manchester alumni who have since gone on to forge remarkable careers at NASA and the European Space Agency. You can find out more about the Buzz podcast at manchester.ac.uk/The Buzz. You can find us on Instagram and Twitter at UOMSciEng, and you can also search for our Facebook page and YouTube account. If you have any questions about today's episode, our email address is fsemarketing@manchester.ac.uk. Bye for now.